What do you think is big? Black holes? Stars? The vast stretches between galaxies? These things push the limit of size as we know it. But what about a number so big that if you tried to store every digit in your brain, it would turn into a black hole before you could even get close? Or, to put it another way, a black hole the size of your brain would store less information than there are digits in this unimaginable number. Pretend there's a contest to see who could write the largest number on a whiteboard. If you went first, what would you write? Maybe you'd go with 999999999, filling the entire whiteboard with nines. That would definitely give you a big number. But here's a trick. If you wrote a bunch of ones instead, you could fit even more digits because ones take up less space than nines. Suddenly, you'd have an even bigger number just by using a more efficient digit. But as big as these numbers get, there are ways to go even further. Imagine using special notations designed specifically for creating unimaginable numbers. One of these methods is Knuth's up arrow notation, which opens the door to numbers that make even rows of nines and ones look tiny by comparison. Knuth's up arrow notation can simply be thought of as a tool for stacking exponentiations. It's a shorthand that allows us to take multiplication and powers to an extreme level, building enormous numbers with just a few symbols. Here is a simple progression of Knuth's up arrow notation. With one arrow, we start with basic exponentiation. 3 up 3 equals 3 to the power of 3, which is 27. With two arrows, the growth intensifies. 3 double up 3 means 3 to the power of 3 to the power of 3, which is 3 raised to 27, resulting in 7,625,597,484,987. With three arrows, it becomes incomprehensibly large. 3 triple up 3 represents 3 raised to itself over 7 trillion times. This result is a number so massive it's practically impossible to express fully. Now, let's take things further by adding just one more arrow, making it 4 arrows, and see what happens. With 4 arrows, 3 quadruple up 3, we start with the result of 3 triple up 3, which as we saw is already an unimaginably large number. Now we take 3 and raise it to the power of that entire result. This recursive structure builds a number so vast that it's beyond anything we could realistically write down or even imagine. Well, if you thought numbers couldn't get any more mind-bending, let me introduce you to Tree 3, derived from a mathematical game involving trees, considered one of the largest numbers that can be meaningfully defined. Even though the universe is full of incredible processes, like the expansion of the universe, the formation of stars, and the collapse of black holes, none of these processes can produce numbers as large as Tree 3. As Professor Tony Padilla puts it, you've got all these physical processes going on in the universe all around you. None of them come close to Tree 3. In essence, Padilla is highlighting the vast gap between the scale of the physical universe and the realm of abstract mathematical concepts. This number isn't just large, it's on a scale that makes everything else seem minuscule by comparison. To understand why Tree 3 is so incomprehensibly massive, let's take a closer look at how it's constructed. We know Tree 3 exists, and we know it's a finite number, but we don't know exactly what it is or how many digits it has. The number comes from a game involving trees, which are branching structures used in graph theory. In this game, you create a forest of trees using building blocks called seeds. Each tree is made by combining these seeds in different colors and patterns. There are just 2 rules in this game. The first rule is that the first tree can only contain 1 seed, the second tree a maximum of 2 seeds, the third a maximum of 3 seeds, and so on. It would look something like this. The second rule is, when you create a tree that could contain a previous smaller tree within it, the game ends. To put it simply, if you make a tree graph that includes the structure of a smaller, earlier tree graph, the game stops. A tree is considered contained within another if it shares the same pattern, with seeds at its ends connecting back to a common ancestor seed in the same way. This matching pattern triggers the end of the game as it appears within the larger tree graph. It would look something like this. The goal of this game is to create as many trees as possible before inevitably creating one that contains a previous tree. At that point, the forest dies and the game ends. To begin simply, let's use just one type of colour or seed. This is called Tree 1. Following the two rules, you can see that after making the first tree, which only has one seed, the second tree contains the structure of the first. This immediately ends the game after just one step, meaning Tree 1 equals 1. Now, let's play the game with two types of seeds. This is Tree 2 using two colours, like green and red. You can stretch the game out to 3 steps. You start with a simple green seed as the first tree. For the second one, you use 2 red seeds in a way that doesn't contain the structure of the first tree. So, the game continues. For the third tree, you can build one with just a single red seed. Remember, the third tree can have up to 3 seeds, but you're allowed to use fewer. However, on the fourth tree, no matter how you arrange the seeds, you'll inevitably create a structure that contains one of the previous trees. This means the game ends here. So, Tree 2 equals 3. You might be able to guess where this is headed. When we play the game with 3 seed colours, the result, Tree 3, reaches an incomprehensibly huge scale. With just 3 seed types and 2 simple rules, you can build trees for the rest of your life, and your descendants could keep going for countless generations. Even if humanity kept playing until the end of the universe, you still wouldn't reach the maximum number of trees allowed without ending the game. You wouldn't even get close to Tree 3. As Professor Padilla puts it, this is just way bigger than anything you could even begin to imagine in physics. Many mathematicians have uncovered fascinating insights into Tree 3 and the tree game. For instance, American mathematician Joseph Kruskal proved that any tree n will eventually produce a tree that contains a previous tree, meaning each tree n yields a finite number. Paradoxically, proving this required tools from non-finite mathematics, including transfinite arithmetic and ordinal numbers. While any given tree n, like Tree 3 or Tree 4, could theoretically be solved with finite arithmetic to show it's not infinite, this process would be inconceivably slow, taking longer than the lifetime of the universe. Ohio State mathematician Harvey Friedman proposed a way to calculate how many symbols, mathematical operations like plus signs, exponents, etc., would be needed to prove Tree 3 is finite. The answer is staggering. It would require 2 up 1,000 symbols, meaning 2 to the power of 2 repeated 1,000 times. This quantity of symbols alone is beyond comprehension, illustrating just how vast and complex Tree 3 truly is. Imagine it took just 1 Planck time to work through each symbol in the Tree 3 proof. A Planck time is incredibly short, about 5.39 times 10 to the power of negative 44 seconds, or the time it takes light to travel a single Planck length in a vacuum. This is a convenient stand-in for the fastest rate we could physically process each symbol. Even at this speed, with each symbol being processed at the maximum pace allowed by the laws of physics, the universe would end before the Tree 3 proof could be completed. And if the proof somehow appeared fully completed in an instant, it would still be far too large to fit within the entire universe's physical limits. The sheer number of symbols required is so vast that not even the cosmos could contain it. I'm sure many of us here may be feeling a little confused or even overwhelmed. When we talk about concepts like infinity or numbers as vast as Tree 3, it's easy to feel as though we're stepping into something beyond the limits of human understanding. We're diving into ideas that stretch far beyond our everyday experiences, concepts that challenge the very frameworks we rely on to make sense of the world. Infinity isn't just a big number, it's boundlessness itself, something that never reaches a final point. And Tree 3, despite its unimaginable size, is still finite, still closer to zero than to true infinity. You see, in our universe we're used to the idea that things have limits. Galaxies, stars, planets, even the observable edge of the cosmos. All these things occupy finite space and have boundaries. There's a beginning, an end, a measurable size. But infinity challenges that idea completely. Infinity suggests that there are no edges, no stopping points, no last number, no final frontier. It's a concept that breaks free from any definition or physical restriction. This can be illustrated by looking at the universe around the periods before and after the Big Bang. There was no before in a conventional sense, assuming time itself emerged from the Big Bang 13.8 billion years ago. However, imagining a state before the Big Bang pushes us to think about infinity as something beyond measurable time or space. Whatever preceded the Big Bang was not bound by dimensions, chronology, or spatial location. It was an undefined state, perhaps a singularity, perhaps nothing at all that we can conceive. This lack of boundaries, no time, no space, no physical framework, suggests an infinity that doesn't have a beginning or end. The absence of edges or constraints in this pre-universe state exemplifies infinity as something not restricted by time or physical limitations. The universe has continued to expand since that moment with no known boundary or limit. This expansion hints at spatial infinity. As the universe grows, it reaches into an endless frontier that does not actually stop. Furthermore, time flows forward endlessly without a clear stopping point or final moment, reinforcing the notion that time itself could stretch infinitely into the future. So both the period before the Big Bang, a boundless, undefinable state, and the expansion after it, an ever-growing universe with no limits, embody different aspects of infinity. If the universe itself is infinite, it means that space extends endlessly, filled with more galaxies, stars, and planets beyond anything we could ever observe. In an infinite universe, every possible combination of matter could exist somewhere out there, perhaps even parallel realities on worlds remarkably similar to ours. Let's consider a thought experiment known as Zeno's paradox, which explores the strange and often counterintuitive nature of infinity. Imagine you're trying to walk to a wall across the room. To get there, you first have to reach the halfway point. But once you've reached halfway, there's still half of the remaining distance left to travel. And when you cover that next half, there's still another halfway point waiting for you. And then another, and so on. Each time you're only ever covering half of the remaining distance. According to Zeno's paradox, if you keep halving the distance endlessly, you'll never actually reach the wall because there will always be another halfway point to cross. The paradox suggests that within any finite space, there can be an infinite number of divisions. It's a strange, almost paradoxical idea. You're trying to reach a finite destination, yet the journey can theoretically be divided into infinite steps. Zeno's paradox taps into a core idea of infinity, that something finite, like a single step, can still hold an infinite number of smaller parts within it. In reality, of course, we do eventually reach the wall, but this paradox highlights the mind-bending notion that infinity can exist within the boundaries of something finite. What if I told you that not all infinities are equal? It sounds contradictory, even impossible. How can something that's endless be smaller or larger than another endless thing? This paradox of size within infinity is at the heart of the work of mathematician Georg Cantor, who revealed a truth about infinity that few people could have anticipated. There are different sizes of infinity, each more expansive than the last. Cantor began with the simple idea of natural numbers 1, 2, 3, and so on. These numbers stretch on infinitely, forming a set that feels endless. But he then turned his attention to a different set, the real numbers, which include not only whole numbers, but also the decimals between them, like 0.1, 0.001, or 0.0001, extending endlessly. Through a groundbreaking approach, Cantor showed that there are far more real numbers than natural numbers, even though both sets are infinite. In other words, some infinities are, in a very real sense, bigger than others. This discovery was as radical as it was unsettling. It suggests that even in the boundlessness of infinity, there's a hierarchy, a structure to what we often consider formless. Cantor's work implies that no matter how large or unending we imagine something to be, there's always another level beyond, another layer of infinity stretching further than the last. It's as if infinity itself holds depths we can never fully fathom, a concept so vast that it forever exceeds our understanding. Countless other, perhaps even more unsettling infinities exist, hidden just beyond their own unreachable boundaries, infinities that reside within us, infinities stretching back into the distant past, and infinities endlessly expanding with even greater infinities. Benoit Mandelbrot, a Polish-born mathematician, in 1975 recognized a fascinating order hidden within the apparent chaos of nature, which he uncovered through a unique geometry he named fractal, derived from the Latin word meaning broken. He discovered that within each fractal lay an infinity of patterns, endlessly repeating yet always subtly unique, suggesting that nature's complexity is boundless and woven within an infinite depth. With fractals, Mandelbrot could quantify the coastlines, model the intricate branching of trees, and even the clustering of distant galaxies. A fractal is a never-ending pattern that is self-similar across different scales. They are created by repeating simple mathematical equations over and over in an ongoing feedback loop. Driven by recursion, fractals are images of dynamic systems. What distinguishes fractals is their self-similarity and scale independence, allowing them to exhibit infinite complexity. No matter how much one zooms in or out, a fractal continuously reveals new layers of detail without becoming simpler, defying typical spatial limits. The Mandelbrot set, a famous fractal pattern generated through simple mathematical equations, exemplifies this notion of infinity by offering endless intricate detail, no matter how deeply you explore it. This brings us to the question, can the universe itself be considered fractal? In certain ways, the universe appears to display fractal-like patterns, particularly in the clustering of galaxies and large-scale cosmic structures. However, on the largest observable scales, the universe exhibits a form of homogeneity. This means that, when viewed broadly enough, matter distribution appears relatively even, contrasting with a true fractal, which retains detailed complexity at every level. While the observable universe does not fulfill the strict criteria for a fractal, some speculate that if we could look beyond our observable limits, we might find that the universe possesses fractal properties in larger dimensions. This remains a tantalizing possibility, as the concept of infinity re-emerges again and again in cosmology, challenging our understanding of the universe's true structure. Therefore, while the universe is not fractal in a traditional sense, it could exhibit similar scale-independent structures beyond our observational reach, extending the concept of fractal infinity to unimaginable horizons. But Tree 3 adds a new layer to everything we've just discussed. It takes these already complex ideas, fractals, Zeno's paradox of infinite steps within a finite distance, and Cantor's idea of different sizes of infinity, and introduces a different kind of vastness. Tree 3 isn't just large, it's a finite number that, despite having an end, feels almost beyond scale. Unlike the infinities Cantor described, which have a kind of order, Tree 3 is a finite number, Yet its scale is so immense that even the largest infinities we typically think of seem small by comparison. Tree 3 challenges us to rethink what big really means, as it doesn't just extend beyond what we can count, but reaches a point that feels beyond comprehension altogether. Tree 3 is finite because, at its core, it's produced by a process with a specific stopping rule. In mathematics, something is finite if there's a point where the process creating it must end, no matter how large that endpoint is. Tree 3 follows a structured process that eventually reaches this endpoint. Unlike infinity, which inherently has no end, Tree 3 results from a sequence of steps that, while immense in scale, will always terminate due to the rules governing it. The finite nature of Tree 3 means it's a concrete, reachable value even if it's beyond practical computation. In contrast, infinity is boundless and does not have an endpoint. No matter how far you go, you're never finished with infinity because it isn't governed by any stopping condition. Tree 3, however, does have such a condition which gives it a specific value and makes it finite even though it's practically inconceivable in size. So where does this leave us? Tree 3 challenges not just our understanding of numbers, but the very framework of human thought. We often think of knowledge as something that expands, growing like a network of galaxies that stretches ever outward. We expect that as we push further, we'll uncover more, understanding layer by layer until we eventually approach completeness. Tree 3 stands as a reminder that there are, in fact, ideas so vast that they defy this model entirely. It suggests that there are forms of knowledge we can recognize but may never fully explore. Philosophically, this brings us face to face with the limitations of human cognition. Our minds evolved to handle the finite world of survival, counting, measuring, and solving immediate problems. The abstract world of mathematics allows us to explore beyond those limits, but concepts like Tree 3 reveal that even abstraction has boundaries. Tree 3 shows us that while mathematics can take us to the edge of what's conceivable, it can also reveal ideas that exist just beyond that edge, ideas we may never fully grasp, no matter how we try. In some ways, Tree 3 mirrors the boundaries of the universe itself. Just as there are cosmic horizons we cannot cross, where galaxies fade beyond sight, where information from black holes is lost forever, there are also intellectual horizons. Tree 3 represents a boundary where our mathematical tools reach their limit, where numbers grow so large that even the largest infinities we typically think of seem small by comparison. It's a concept that exists purely because we have the power to imagine it. Yet it reminds us that some forms of imagination can't be fully explored or expressed. This boundary isn't just a limit, it's an invitation to wonder. Tree 3 encourages us to think about the nature of understanding itself. If there are other concepts we cannot fully comprehend, does that limit our potential, or does it inspire us to reach further? Mathematics, after all, is filled with ideas that seemed impossible until someone redefined the rules. Perhaps Tree 3 is a reminder that the most profound ideas are those that lie just out of reach, urging us to keep pushing, to keep questioning the boundaries of what we know. In a universe that is already beyond vast, Tree 3 shows us that there are still greater scales, greater limits to explore, not in time or space, but in the power of thought. It's as though the concept itself points to something uniquely human, the ability to envision what lies beyond, even if we can never quite reach it. In the end, Tree 3 is more than a number. It's a testament to the idea that some journeys are intellectual rather than physical, and that true exploration may lie in realizing just how infinite the questions can be.